Okay, part two of periodic trends, physical and chemical properties of the alkali metals and the halogens. Now, as problematic as IB can be, they are really good about being very, very specific about things that you need to know. And so when we look at the entire periodic table, there's so much information that we could derive from it. IB is earmarking just a couple of parts of the periodic table to investigate a bit further. So we're going to be looking at just just the alkali metals and the halogens and investigate and compare their properties. Now, a couple of things though. You may have noticed in talking about the alkali metals and the halogens, there's a few elements that we ignore. Francium, astatine, tennessine, these are elements that are just extremely rare, and so by and large we just omit them from discussion. So when we're talking about the alkali metals, it's lithium through cesium. Talking about the halogens, it's fluorine through iodine. Okay, first, the alkali metals. The alkali metals are the most reactive family of metals. You're never going to find any of the alkali metals, sodium, potassium, rubidium, by themselves. They're just too reactive. They're going to be part of a compound, usually in a rock, an ore, something like that. They have to be extracted, isolated separately. Bonded by relatively weak metallic bonds. Now in our next unit, we'll talk a lot more about bonding. That is the unit, bonding. But for our purposes today, we will need to address a couple of the bonds that are responsible for the periodic trends that we're going to be observing. So I'm going to show you a short little video here on metallic bonds, just enough to reacquaint you with what a metallic bond is.
Metal atoms have few electrons in their valence shell, and these are relatively weakly held. Though metal atoms group together in a crystalline lattice structure, they have very different properties to the ionic solids. For example, solid metals are able to conduct electricity. This is because the loosely held valence electrons of metal atoms are delocalized. They are not bound to one atom. Instead, they can move through the lattice in all directions. A sea of delocalized valence electrons surrounds the crystal lattice of the cations.
All right, so that's really all that you need to know for our purposes. So what the atoms here represent are metals, and the metals lose electrons, their outermost electrons, to this what we call a sea of electrons. In the case, that sea of electrons is negatively charged, so it's going to be attracted to the metal cations, and that itself is what is called a metallic bond. And it's one of the reasons that metals are malleable. You can bend metals because this sea of electrons, kind of think of it like a glue that holds it together, can move with the atoms. Again, more on this later in our next unit. Melting and boiling points decrease as you move down the family. We're talking about the alkali metals, due to the weaker metallic bonds as the atoms get larger. So going from lithium down to cesium, the atoms get bigger, as we know. Well, as the atoms get bigger, it means that the nucleus, the positively charged nucleus, is going to be further and further and further from the sea of electrons that holds the atoms together in a metallic bond. So the melting and boiling points decrease as the atoms get larger, or as we go down the family. Now, melting and boiling points are often referred to kind of interchangeably. Sometimes they'll mention melting points and then boiling points, but the trends, of course, they're different, but the trends are the same. So it's a nice little diagram of this. The blue represents boiling points. You can see as we go from lithium to cesium, go down the family, the boiling points get smaller and smaller and smaller, and the same thing for the melting points, smaller and smaller and smaller. And for both cases, it's the metallic bonds that are being broken. So know this trend. Melting and boiling points decrease as we go down because the atoms get larger. Now that's going to be true for the alkali metals. Is when we get to the halogens, you'll see it's just the opposite. Chemical reactivity increases as you move down the family. Again, talking about the alkali metals. As the atoms get larger, their valence electrons are more easily lost. The alkali metals, when they react, they do so by losing their one valence electron. The larger the atom is, the more easily it is able to lose that electron. Remember, ionization energy decreases as we go down a family because it's easier to remove an electron. So cesium is going to be much more reactive than lithium because cesium is going to be able to get rid of its electron, its valence electron, much more readily. So the reactivity increases as we go down the family. I'm going to show you a little video now of that reactivity.
There are 6 alkali metals: lithium, sodium, potassium, rubidium, cesium, and francium. They're all soft metals which can be cut with a knife. In air, the elements quickly become coated with compounds that form on the metal's surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal surface can be seen. But this time, corrosion occurs even more quickly. With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly with air. Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Let's see an equation for the reaction. Hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our 5th alkali metal.
I like how he says that reactions get more terrifying as you go down the family. Okay, now when the alkali metals react with water, there's a very specific chemical reaction that you're responsible for. Okay, so let's let X represent any of the alkali metals. When it reacts with water, it's going to form hydrogen gas, and that's what caused the flame. The heat that was given off in the reaction caused the hydrogen gas to burst into flames, and a base. Balance the equation. So this is a basic solution. Remember that hydroxide, well, you may not have gotten the acid-base unit last year, but we will have a big unit on acids and bases. Any compound that contains a hydroxide ion is a basic solution. So you are responsible for being able to write a balanced chemical equation with any of the alkali metals reacting with water, and it's exactly as you see it here. It'll form hydrogen gas, which is diatomic, and a hydroxide, so sodium hydroxide, potassium hydroxide, lithium hydroxide, hydroxide. Okay, now let's look at the halogens. It's the most reactive family of non-metals. So remember, the alkali metals were the most reactive metals, and halogens the most reactive non-metals. All are diatomic molecules bonded together by very weak dispersion forces. Now again, like the metallic bonds, we will go into dispersion forces in our next unit on bonding, but let me show you a little video clip here, just enough so that you kind of reacquaints you with what we mean by dispersion forces. It's the attractive force between diatomic molecules, or molecules.
The diatomic molecules of halogen elements are non-polar because the component atoms are joined by a symmetrical covalent bond, characteristic of molecules made up of atoms of equal electronegativities. Non-polar molecules can attract each other only by means of dispersion forces. Random motion of electrons in the electron cloud surrounding a molecule can result in an instantaneous separation of charge. One part of the molecule becomes positively charged, while the other part takes on a negative charge. The more electrons a molecule contains, the more likely is the formation of such instantaneous dipoles. A momentary dipole in one molecule can induce a dipole in a neighboring molecule, the two dipolar molecules attracting each other for a short time.
Okay, and that's what we mean by dispersion forces. We have nonpolar molecules, but by virtue of the electrons just moving around, we have temporary dipoles. So one part is positive and the other part is negative, which means that it'll be attracted to its counterpart. And that's what occurs with the halogens, the diatomic molecules of the halogens. Melting and boiling points increase as you move down the family due to the stronger dispersion forces between the increasingly larger diatomic molecules. So as you can see, it's drawn to scale here. The atoms or the molecules, diatomic molecules from fluorine down to iodine get larger and larger and larger, which means you have more electrons moving around. The larger the molecule is, so the greater the dispersion forces. Now, dispersion forces are the attractive force between the diatomic molecules. So fluorine here, it's diatomic, two fluorine atoms covalently bonded, and that's what's represented here. So it's going to have an attraction for another fluorine molecule. That, depending upon the strength of that attraction, the substance could be a gas, a solid, or a liquid. When we talk about something about the halogens melting or boiling, we're talking about breaking the dispersion forces. Since the dispersion forces are greater for larger molecules, the melting and boiling points increase as we go down the halogens. Remember that fluorine is a gas, chlorine is a gas, but bromine is a liquid. So bromine is large enough so that it has enough dispersion forces between its molecules to have it become a liquid. And iodine is larger still, and so it has enough attractive force between its molecules that it's a solid. So you might look on your periodic table, fluorine and chlorine are gases. They don't have enough electrons to form a strong enough dispersion forces to attract them together, at least not at room temperature. But bromine does, it becomes a liquid, and iodine a solid. And like we saw with the alkali metals, we can see the trend for both boiling and melting points increase as we go down the family from fluorine, chlorine, bromine to iodine. They both increase. So this is exactly the opposite as the alkali metals. Remember, the alkali metals, the melting point decreases as we go down the family. Chemical reactivity increases as you move up the halogen family. As the atoms get smaller, electrons are more easily added to complete their valence shell. So here we're not talking about the halogens in respect of them being diatomic molecules, but just the individual atoms. So fluorine is smaller, and so it's going to be able to attract electrons much more readily than iodine. Remember, the attraction for an electron is due to the positive charge of the nucleus. And fluorine, because it's smaller, the nucleus is going to be much closer to any electrons that might come into its vicinity. Whereas iodine is much larger, and so any electrons that comes into its vicinity is going to be much further away from the nucleus. So the chemical reactivity increases as we go up the family. Again, just the opposite from alkali metals. Okay, now let's look at an example, single replacement reactions. Now you learned about single replacement reactions last year. When we get to our unit on stoichiometry, we'll revisit it. The only thing that you're responsible for any of this stuff is how it relates to periodicity. So let's look at what would happen if chlorine gaseous chlorine was bubbled into an aqueous solution of sodium fluoride. Well, if we look at the halogens and the reactivity, we can see that chlorine is more reactive, or is not as reactive as fluorine. So it is not going to be able to replace fluorine in the reaction. So there'll be no reaction here. But if we bubbled chlorine into, excuse me, into a aqueous solution of sodium bromide, well, chlorine is more reactive than bromine, so this reaction will take place. And you might recall that in a single replacement reaction, you have one element by itself replacing another element in a compound. And it'll always be like will replace like. So chlorine is a halogen, so it's going to replace bromine, which is a halogen. And then to balance the equation. So we can tell this reaction will take place because chlorine is more reactive, or is more reactive than bromine. This will not take place because chlorine is not more reactive than fluorine. All right, now there's one other thing that you need to know here. Sodium bromide and all compounds of all halogen compounds are going to will not have a color. Well, ionic compounds will not have a color, but bromine does have a color. Bromine has an orange-brown color. So in this reaction, you would actually see something happening. In the first reaction, you wouldn't see anything happening. Let's say that you had sodium fluoride here and you bubbled chlorine gas in here, nothing would happen. There would be no color change at all. But in the second reaction, if the solution was sodium bromide and you bubbled chlorine gas into it, well, then you would begin to see the test tube would start turning this orange-brown color of bromine. And this is actually something that you need to know. In the case of the formation of a halogen, a color will be produced, and you can use that color change as an indicator that a reaction took place. So this reaction, no color change would take place because no reaction took place. This one, a color change took place because you formed a halogen. Note, a nonmetal that is more reactive than another is called is the stronger oxidizing agent. That's just a term that you might hear or see in one of the tutorial videos. Don't worry about that. That's something that we'll talk about when we get to our unit on oxidation reduction. An oxidizing agent just means that it's able to pull an electron away from another element. You need to know the colors of the halogens. And here we're talking about the diatomic molecules. So fluorine is a yellow gas, chlorine is a green gas, bromine is an orange-brown liquid, and iodine is a purple solid. Although halogen compounds are colorless, these colors will appear whenever a halogen is formed, meaning the diatomic molecules. And by the way, anytime you hear reference to a halogen being formed, it'll always be the diatomic molecules. Okay, now we're going to look at period 3 oxides reacting with water. So again, IB is just bookmarking a couple of things for us to look at in more detail. So we just looked at the alkali metals and just looked at the halogens. Now we're going to look at period 3 oxides. What do we mean by that? Well, just as you might think. Sodium oxide, magnesium oxide, aluminum, silicon, phosphorus, sulfur, chlorine, all oxides. So when we react these or place these into water, what will happen? So there's a series of chemical equations that you're going to be needing to know. Okay, now we can break these into 3 parts. The first are the metals. Sodium and magnesium are metals, and so these are metallic oxides. Whereas the last 3, these are nonmetals, phosphorus, sulfur, chlorine, non-metallic oxides. The 2 in between are a little problematic, and we'll talk about them at the end. These are amphoteric oxides, and they won't react as metals or nonmetals. It depends upon the situation that they're in. Amphoteric means that they can react as either an acid or a base. You'll get notes on that in just a second. Okay, so first let's look at sodium and magnesium and see what happens when they react with water. Oh, I will be putting a link on today's lesson module for this video. It's a really, really good review of everything I'm about to go over. So if you'd like some more discussion on it, please look at that video. He does a really nice job. Okay, so metallic oxides form basic solutions. So sodium oxide reacting with water is going to form sodium hydroxide. Magnesium oxide and water will form, you guessed it, magnesium oxide. And these are basic solutions. They're aqueous. Anytime you have a hydroxide in solution, it's going to be, or hydroxide as part of an aqueous solution, it's going to be basic. Okay. You also need to know that when something is basic, it means that its pH is going to be greater than 7. I don't think you got to the acid-base unit last spring. We will have a big unit on acids and bases, and so stay tuned for that. But for right now, just be aware that the pH, which is the acidity-basicity scale, if the pH is less than 7, then the solution is, if the pH is greater than 7, then the solution is basic. So I hope you're understanding you need to be able to write these equations. So if I say you'll write a balanced equation for sodium oxide and water, you need to be able to write that. Okay, now let's skip over to the non-metallic oxides. They form acidic solutions, so phosphorus, sulfur, and chlorine. Now what I'm going to show you here are just a selection of different oxides of those three. They combine together. You might remember that covalent compounds can combine together in many different ways. You know, we have those prefixes that we use to name them, like tetraoxygen dioxide, sulfur decoxide, things like that. So I'm going to give you just the ones that you're responsible for. Okay, so this is tetraphosphorus decoxide reacting with water. This is going to form phosphoric acid. So an acidic solution. So nonmetallic oxide and water forms an acid. Sulfur dioxide and water will form sulfurous acid. Sulfur trioxide and water will form sulfuric acid. And then we have chlorine, dichlorine monoxide, and water will form hypochlorous acid. So again, the nonmetallic oxides that I've chosen here are just a random selection. These are the most common. And these would be the only 4 equations that you'd be responsible for, and most likely the only ones that IB would hold you accountable for. And by the way, the sulfur oxides, these two, we'll be revisiting these when we get to our unit on acids and bases. This is what's called part of what's called the contact process. It's the production of sulfuric acid. Sulfuric acid is the #1 most mass-produced chemical in the world. Acidic solutions will have a pH less than 7. So you need to know that. So a common question that IB could ask is which one of the following reactions will form a pH less than 7? So all you would need to do probably for that is recognize which one is a non-metallic oxide. So all of these are non-metallic oxides. They react with water, they will form acids. pH will be less than 7. All right, now the last two, aluminum and sulfur, aluminum and silicon, a little bit more problematic, not quite so easy. Okay, both are amphoteric oxides, and the term amphoteric means it's able to react as an acid or a base, depending upon the conditions. Okay, so let's first look at aluminum oxide. If we were to put aluminum oxide in water, we would be disappointed. It's insoluble. Nothing would happen. However, if we reacted, however, it will react as an acid when added to sodium hydroxide. Sodium hydroxide is a very strong base. So in this case, it will behave as an acid. So aluminum oxide reacting with sodium hydroxide and water will form this compound. This is sodium aluminate. And to balance it. And it will react as a base when added to hydrochloric acid, which is a strong acid. So in this case, the hydrochloric acid is the acid, it will behave as a base. So again, amphoteric is able to react as an acid or a base. Here it's reacting as an acid. Here it's reacting as a base. Again, you'll have to stay tuned to our unit on acids and bases to have a better understanding on what's going on here. You don't need to know that. You just need to know these reactions. So in the last reaction here, it'll form aluminum chloride and water, and to balance it. Okay, so aluminum oxide by itself with water, no reaction, but if you place it into sodium hydroxide, this reaction will take place. If you place it into hydrochloric acid, this reaction will take place. And last, silicon dioxide. Silicon dioxide and water also, nothing will happen. However, it will react as an acid when added to sodium hydroxide. And this will produce sodium silicate. Balance the reaction. Okay, now in this case, silicon dioxide is behaving as an acid, so you might think that it would also behave as a base, but it doesn't. It will not react as a base. So this is the only reaction that you're responsible for silicon dioxide. Okay, guess what? That is the end of Unit 1. The end of notes, the end of Unit 1.